Okay, I think we are back here. Sorry about the temporary hang up. Okay, I shall continue now. Can you see my screen? Just to confirm. So can I continue now from here? Just to check, can all you hear and see the screen now? Okay, Ken, thank you. So I continue from where we stopped just now. Sorry for the interruption. Okay, we are here at the full wave bridge rectifier. Right, just now I just mentioned I was cut off halfway through. So as usual, this will be your so-called input on the left-hand side, your AC. This will be your so-called input signal. All right, this one. Okay. And at the output, of course, of your rectifier, you will get power of the full wave so-called reproduction of the AC, which is DC. Okay, so the left is AC, the right is DC. Okay, but of course, this is not the actual DC yet because you still got to go through the filtering circuit and the regulator. Okay, this part is only after the rectification, just to clarify. We are only talking about rectifier here, and that is the output of the rectifier. Okay, okay, can if all right, move on. Okay, so now we try to understand the diagram a bit more and see how it operates. Okay, so we first start off with the positive cycle, all right, or the positive half cycle operation of the AC. Okay, here they mentioned that D1 and D3 will be closed or conduct when the positive cycle comes in. So now we go back to here. What does it mean? It means here it is positive. All right. This one will be forward bias D1. Okay. And then continue from here. I go past through R.
Hello, everybody.
Hello. Go through R and then come down to D3. Okay. So the flow
Anas
of the
Mustafa.
positive.
If you hear me, please reply. Anas Mustafa.
Okay. Okay, so the positive comes to here, forward bias D1, the current flows through here and go through your R and then continue with your D3. All right. And then, of course, return back to this side, the source. So for the positive half cycle of the rectifier full wave, D1 and D3 will operate. Okay, so the current flow through the way I just showed you, go through D1, go through R, go through D3 and back to the source, the original source. Okay, Ken, that is your positive cycle. All right, here actually they so-called cut off the part of the circuit to show you exactly what I just told you. All right, this one forward bias. Right, forward bias, because positive go to positive, forward bias, current flow through. Same thing here, also forward bias. That's why current can go past here, D3 and back. So it's just flowing through two diodes. So basically D1 and D3 are forward bias. Okay? And now obviously the D2 and D4 is reverse bias. Okay, how? Because when your positive comes here, your negative of the diode is here. So it's reverse bias. Current will never pass through here. D2 will never come through here because it's reverse bias. Yeah. Okay. So same for the D4. Positive comes here, I cannot conduct. So D2, D4, they are reverse bias and or rather open. So there's no current flowing through there. So the only way the current can flow through is through D1, past the resistor, and then D3. Okay, then that's for the positive half. Okay, just to reiterate again, positive half. Okay. Then, of course, after having explained the positive half, we now look at the negative half cycle of the AC. Coming in and see what happened. All right. So imagine now the negative cycle is coming in here. Okay, so negative coming here. Now, just now it was reverse, but now negative and negative is forward bias for this diode D2, right? Correct? And then I continue, I forward bias for D4. All right, and the current flows through. But now the flow of the current don't flow in the manner that I just showed you. It goes from positive to negative. So in that sense, you still flow through R in the same way as just now D1 and D3 does. Okay, so the current will flow through this way. The current flow from positive to the negative end. All right, so the same direction of the current flow through are here, positive, negative. Because now D2 and D4 is forward bias. Just now was D1 and D3. Are you okay? Okay, that is for the negative half cycle of your AC. These two will conduct. Okay, so during the positive cycle, D1, D3. Negative cycle, D2 and D4. Okay, can I highlight, underline the keyword for you? Yeah, D2 and D4. Okay, obviously they conduct because they are forward bias. All right, reverse bias, no current can pass through. Then, this one is the same thing. I feel VDC is still 0.637 Vm. Okay. Any question? I pause for a short while to clarify for the bridge rectifier. Anyone? Anybody wants me to repeat anything or clarify any point I just explained so far for the bridge rectifier? Zhen, any question? Or Jessica? Okay, Ken, thank you. Okay, sure. Thank you. Okay, if not, then I continue. You realize that this topic is quite a lengthy one, so yeah. But I still prefer you to understand rather than not too sure, because this one concerns your practical also. Yeah. Okay, so just quickly summarize just how I mentioned. I'll come back to the original circuit. This is your full wave rectifier circuit. Okay. Very quick one. During positive cycle of the AC, D1 and D3 will conduct. Okay, then it will flow. Okay, this is for the positive cycle here. Okay, then when the polarity reverses, the negative cycle so-called come in, then D2 and D4 will conduct. Right? Then you'll get another positive cycle here. Okay, the positive half is because both the current flows through the same manner, same direction. Okay, flow through this way. Okay, both also flow through this way. Okay, that's why you get one half positive, this half also positive. And then, of course, you repeat the same thing. Okay, so in other words, the positive and negative cycle comes in are being rectified now to give you a waveform that is such. Okay, this is after rectification. As I mentioned, I repeat, we are only doing rectifier now, only rectification. We haven't come to filtering yet. So this is what you will get after the rectifier, this waveform. And it's full wave. Why we call full wave? Because we rectify both the positive and the negative half to get both positive half here. Okay? For one cycle of the AC, we get this one as in DC. That's why you can see VM here. Basically, we are actually in DC. Okay? That is the conversion from AC to DC. That is your purpose of your rectifier. All right, so I just quickly summarize again. So we move on. If you have no question to the how the current flows and when it flows, when it forward bias and reverse bias, okay? Okay, of course, very obvious, just now you saw, you don't need a transformer, all right, to be center tap, right? We use rectifier to do the conversion, which is all the diodes, the 4 diodes there, okay? Now, of course, current rating is lower because basically diode is a very low current component, right? All right, then of course, meaning of course, if you are using components like diode, the cost of course will go down or cheaper. Okay, because I don't need such a huge transformer anymore. Again, so these are advantages of a bridge rectifier. Okay, good. We have settled that already. Now we move on to the next stage. All right, which is the filter. Okay, the filter. If you have forgotten just now or haven't came in to join earlier, I go back to the very initial block diagram for the benefit of those who are not here early on or miss out. Okay, we have already done rectification here. All right, you just saw. Okay, so we are now going into a filter circuit or filtering. Okay, before we move to the last stage of voltage regulation. So now, just to let you know that we are actually coming into the filter. And just now the waveform you saw, we call it a pulsating DC. Okay? So I continue from there. Okay, so I show you already where is the next circuit or stage of the power supply, which is a filter. First of all, what does the filter do? It actually smoothen out the pulsating DC. Okay, all right. How it happened? Maybe we take a look. Okay, it does have a capacitor here. Now, this capacitor is the one that is trying to smoothen out the so-called pulsating DC voltage. Okay, by charging and discharging. All right, that is what it means. All right. So what happened is after this pulsating DC go past to the so-called filter, this is what you get here. All right, here. Okay, just to show you. All right, so this is just how the original coming in AC. All right, and then this one without. They say without. I haven't filtered yet. Imagine, let's say you come in, you have this waveform, but this only half wave. Okay, after the filter or the action of the capacitor, you have this waveform here. Okay? Yeah. All right, I think this is better than reading the notes because, yeah, you read, you may not able to interpret or comprehend. So here, I repeat again, coming in AC, after that, go through rectifier, then now coming to your filter. All right, your filter will do something like this. This is the bold outline of this wave here on the top. Is actually the action of a capacitor. All right, I think that I did explain to you, right? The nature of the capacitor is basically charging and then discharging. Okay, I keep repeating itself like that. Okay, you look carefully, it's something like the behavior of a capacitor. Okay? Then, Now, of course, you look carefully, this is another circuit. All right. They still call it a full wave, but now they add in a capacitor here. Right? Remember just how we don't have, now we add in. So just how we stop here only, stop at here. We only have the rectified waveform, but it's not filtered yet. So now we add in a capacitor as a filter. All right, over here they put here in case you, yeah. So after this filter, just how I mentioned, just how the earlier diagram, you will see something like this. Okay, they call it the ripple voltage. It's like a small ripple, a small little wavy thing. All right, here. Okay, this is what I mean. Okay, there's a ripple voltage up there after the filter rate. Okay, this is what you want to achieve lah. Because the rest you ignore it. I don't want the rest of the waveform. I want the so-called the top part of the waveform. Okay, which now appear to look like a ripple, like the current on the water. Okay, they call it ripple, that's why. So it's peak to peak. Okay, can? So this is what the filter will do for you. Yeah. Here is just some explanation of the charging, discharging, so not to worry. The main thing is you must know how to identify when it's done by a filter, how the waveform looks like. Okay? The moment you mention the word filter, just remember they will give you the top part of the waveform, which is the ripple voltage, or V peak to peak ripple. Over here, I just circle here. Okay? So you move on. After that, they also start to tell you that there are different type of filter. That's about it. So not to be too concerned. So here they introduce you the so-called the pi filter or the RC. So basically the circuit looks like that. Just now we only have this. Okay? Yeah, the further, just now before you come here, is a very basic. We have the capacitive filter, but now they say there's another type of filter, so they add in this. Okay, R and C. Okay, all right, just an additional, not to worry. Of course, here they tell you also why you want to add in. Example, why you want to add another to pass as much of a DC component of the voltage developed as possible to the first capacitor. Okay. So that of course you hopefully get a more smoother so-called ripple. Okay, that's the purpose. Okay, that's another type. So now maybe here you take a second look. Maybe it will help you understand better. This is good for you because now visually you can see this is what we are talking about earlier on with only one capacitor, right? As a filter. So you get something like that, the ripple voltage here at the top, okay? Which you quite obviously can see that this peak to peak or the VRMS here is thicker or the value is higher than the one on the right, correct? Yes, you look at this, I circle and this. Obviously, so that is the purpose to add in another RC circuit, or rather here, sorry. Erasers. Okay, here. I draw wrongly. Yeah. Now you add in this and you start to get this. Okay? So it's true, you actually try to get it as flat as possible, basically, right? Because ultimately your DC will be a straight line. That is what you want to achieve. So this is an additional circuit, that's why they say. To even smoothen the ripple voltage further in that sense, all right? From slightly higher to even a smaller peak to peak. All right, this voltage, yeah. Okay, Ken? Any question first before I move on? Anybody? regarding the filter now. We are talking about filter now, right? Any question on the filter? Oh, okay, can. We take a 5 minutes break, a short break, then I continue. Okay, shall we continue a bit more? Just to confirm, you can see my screen and hear my voice. Okay, can I continue now? Shall I continue now? Just to confirm, can all you still hear me? Thank you, Jessica. Okay, I will continue from here. All right. Number 4 here mentioned the 3 points that we just talked about just now, right? Okay, because the ripple, talking about the ripple voltage. All right. Okay, the pulsating has a very high, just now we mentioned. So that's the purpose of the filter, is to reduce this so-called the amplitude of the ripple. Okay. Yeah. Okay, that's what I mean, reduce. All right. Then of course, finally, of course, with the half wave, or rather the AC ripple is also much lower than the half wave or the full wave compared to the half wave. Okay. Okay. Now we move on to the next thing. Okay, you're not sure, then I go back a bit. I show you what it means. Okay, for the full wave, the ripple looks like this, the ripple voltage. Okay, very close and very low. But if it's a half wave, it's what we saw just now in the example given. Not this one, this is a full wave. This one. Okay, they are talking about here, the one I circle here. Okay, much larger, higher the amplitude, compared to the full wave, because this is a half wave. Okay, the rectification is halfway only one half. So negative half missing. So this is what you get, okay, at the output for half wave. So in other words, the ripple voltage is much higher. All right. So the full wave is better, of course. The ripple is much smaller. That's what you mean here. Okay. All right. We come back to here. Okay. The next one is almost the last part of the power supply. We talk about voltage regulation. All right. Of course, just now before I started, we also have a very quick understanding of voltage regulation. Now, basically, voltage regulation means keeping a voltage constant or stable at the output. Okay, which is very important in power supply. Okay, you cannot have a power supply where your voltages fluctuate. Fluctuate means what? Go up, go down, and that means not stable. Okay, if it's supposed to 5 volts, it's 5 volts. You cannot suddenly drop to 3.5, for example, or goes up to 6.3 or whatever. Okay, so voltage regulation comes in to maintain the voltage at a constant value, or whichever value you want it, but it has to be constant there. Okay, so what is affecting so-called fluctuation here? We take a look. First, of course, this one beyond our control. Now the incoming 230 volt AC fluctuates. Okay, all right. Then it affects our power supplies. Don't forget we have to convert the AC to DC. So if the AC, so-called the input fluctuate, the DC will be affected. Okay, that's what I mean, or that's what they mean here. Changes in the AC input. Okay, input comes in, change, output obviously will change. That's what it means. Okay, so that's why the word unregulated means fluctuation. Or that's not regulated means not stable. In other words, there are changes. The second point they mentioned is the load condition. Okay, what is the devices that you are connecting to? Maybe there's some fault with the device. Okay, it can be a motor, it can be a laptop or whatever. Okay, that's what they mean by the load condition. May not be good. Okay, so it will also affect the output voltage. Okay, so this is two that you take note. Okay, that is called line regulators. All right, so the next one is voltage regulation. Okay, first of all, repeat again, voltage regulation, make sure your output voltage is constant. Okay? Even if your current goes up and down, it doesn't affect it. Your voltage must be constant. That's what they tell you. Okay? Whether your current goes up or goes down, my voltage still maintains. That is an important one here. That is talking about voltage regulation. Okay? So they mentioned that there are two important factors that affect voltage output. Right? Basically the line voltage and the fluctuation output current. Line voltage, just now we just mentioned these two. Okay, this one, these two okay, these two here. All right. Fluctuation output current, we're coming to it. Okay, in a practical regulator, the output voltage under load is lower than the no load voltage. No load means the device is not connected there. Okay. Okay, so they said in a practical regulator, the output, I repeat, output voltage under load, okay, is lower than output with no load output. Okay, so this is what they say typical. Okay, of course this is what you call perfect right? But you can in the real world you will never get the perfect regulation. But of course we will try to close this gap. Yeah. Okay. So with the load you can see here is like this, right? That's why the say is lower. Okay, no load. Yeah. The V load here is lower than the no load. No load is actually the perfect regulation. Okay? Can so take note of this just in case. There's no perfection one. On paper, everything is perfect, but come to practical, there's some slight differences. Okay, but of course, they try to close the gap. Okay. So they say if you are talking about perfect regulator, the ratio is supposed to be 0. Okay, so the smaller the ratio, the better will be the regulation. Okay, so this value here or formula that give you to calculate the percentage in, or rather regulation in percentage, this value as low as possible. That means it's good. Okay, and here they are given what they represent here. VCC is the open circuit output voltage. Okay, OC, open circuit. Okay, minus the V loaded output voltage. Okay, so having minus the open circuit voltage minus the low voltage, you divide by the low voltage multiplied by 100%, that will give you the ratio or the amount of voltage regulation in percentage. Okay, so repeat, the value smaller, the better. Okay, here already they say, okay, smaller ratio, better. So this value shouldn't be high. Yeah. Okay, so this is how you calculate your voltage regulation. Take note of this formula. I believe during your practical, you may use this. Okay, we move on. Okay, now we talk about the types of voltage regulator. All right, so there are basically two types. One is a series regulator, one is the shunt. The word shunt sometimes means parallel. Okay, just to share with you. Okay, so take note of these two types. Okay, now we take a quick look first. Don't worry if you can't catch, I will still come back during the next lesson to look at this again. So I quickly run through this part first, give you some idea. Okay, in a shunt regulator, the current control element is connected in parallel, just like I mentioned, right? A parallel actually referring to this. So they are talking about this control element is parallel to your load. Okay, this is your load, RL. Okay, that's what they mean. Okay, if this is the arrangement or this is the connection, we call it a shunt voltage regulator. Okay, the word shunt, I repeat, you can take it to mean parallel. Okay, so now that is just a overview block diagram, but the circuit looks like this. Okay, and now suddenly you see something, right? This control element actually is referring to this very powerful component. I'm not sure anyone can tell me what is this. Anybody? Can someone make an attempt? What is this component called? Anybody? What is the component that I just circled known as? Anybody? You probably have seen it before last year. Can recall? Anyone? This one? The one I just circled here, which they call the current control element. It looks like a diode, yeah? It's a diode, but what kind of diode is that? It's a very special type of diode. Yeah, very special type of diode. Yeah, correct, Jessica, you're right. So that's a Zener diode, yes. Now, Zener diode is very common. Okay, you all must know by now. Used as a voltage regulator. Okay, because it has very special characteristic. It operates in the reverse bias condition, opposite of a diode. Okay, but somehow, because of that special characteristic, it's able to maintain a very stable voltage at the output. Okay, so this is a Zener diode used here as a control element. And I just mentioned Zener diode operates in the reverse bias characteristic. Okay, opposite of the diode. Okay, so that's why you see that the negative sign is here, the positive sign is here. Okay, and you look carefully, positive is here, negative is here. It's potentially exactly reverse bias. Okay, but that is the whole purpose of Zener diode. Okay, to give you a very stable or constant output. All right, okay, now we move on. Okay, here they did tell you. Of course, some of the uses of resistor you all know, right? To prevent excessive current from killing your diode or Zener diode. Yeah, sometimes there's a surge in current or whatever. Okay. So they mention this output voltage at the RL, let's say, is actually the same voltage as a Zener diode. Of course, Zener diode come in various voltages. It's up to you to choose. Okay, how many volts you want? You can have 6.8 volts or whatever, 5 volts or whatever. Okay, you choose the rating that you want, and then they will maintain that for you. Okay, example, if I choose a 6.8 volt Zener diode, my output will be 6.8 volts. Okay, hardly fluctuate or hardly change, so it's very stable. Okay, just as I mentioned, whether the current increase or decrease, my output voltage will remain constant. Okay, this is what I mean here. I just mentioned output voltage. Just take note, equal to the Zener, yes. It depends on what you choose. Okay, they have different voltages or ratings, so you choose. You are the designer, example. You want 6.8, you choose a Zener diode with 6.8 volts. You want 5 volts, you choose a Zener diode with 5 volts or whatever. Okay, that's what I mean. Okay. Okay, I think a bit more before we stop here. After this series, we will stop. Okay, one more before we move on. So here, obviously, they call it a series regulator because your control element now is in series, not parallel with your loop or RL. Okay? And now you look at something very different. Suddenly something more complicated appear. Suddenly you see something like this. All right. Okay, there is another component here. Okay, first of all, to identify the component here, this is the amplifier circuit. Okay, but they are performing something different. Okay, if you look carefully, there's a V reference here. Okay, and I have a VS here. So this VS will always compare the voltage with the reference voltage. Or whether it go up or go down, it will start to affect this control element. Okay, understand? Okay, so the change, that's why the arrow pointing here means the voltage here can change. All right. Then, but this voltage Vs that change, I will always compare with a reference voltage. Okay, what to do? Example, if it's going high, then what I should do at the output here? If too low, then what should I do? Or just like controlling a tap. Too much water, I turn backwards. Make sure the tap don't flow too much. Not enough water, I turn the tap more to let more water flow in, example. So there's a control element here. All right. Okay. Indirectly also controlling this one. There's a series control element is over here, but this is also acting as something that is telling the control element when to do what changes. Okay. Okay, here they mainly tell you what are the 4 blocks here: sampling, sense the output voltage. Just now mentioned. The sense one is here, VS. What is happening at the output voltage? Then after that, reference voltage is one, VF. Okay, then you compare, right? You compare here. This is sometimes you can call it a comparator. All right? Yeah, here they write already. Comparator to produce, they say error signal. Okay, actually it's just a feedback, whether things is okay or not. Not okay, then they do something. The control element will do something. I mean, the next one. Okay, the control element will rectify the error. That's why I said too high, you make it lower, too low, you make it higher. Like adjusting, you know what I mean? Okay. So this A here is comparing the changes. Any changes, I tell the control element, okay, to correct it, so to speak. Or adjust it higher, adjust it lower, or whatever. Example. Okay. Can any question up to here? Let me see. Okay, I think we'll stop here today. Okay. Before you all sign out, any question? Any question? Because I don't want you to attend the quiz now because it's quite a lengthy topic, so we have to finish up first. Yeah. Okay, any question as of now? Any question? Final question before you sign out? Okay, Ken, if you have no question, you can sign out. I will see you in the next session. If you have, you can hang on and ask me, no issue. Thank you very much for your attention.